This program is brought to you by Stanford University. Please visit us at stanford.edu.
This presentation is delivered by the Stanford Center for Professional Development, providing graduate-level education to working professionals, online, on campus, and on-site. For more information, please visit study.stanford.edu.
All right, so now I'd like to introduce today's speaker. Today we have Ian Buck from Nvidia, and he'll be speaking about general purpose computing on the graphics processing unit. He's working on the GeForce 8800 CUDA technology, and he'll be speaking to us about the various things they're doing at Nvidia now. His background is he started off at Princeton, where he got a bachelor's degree in computer science, and then he came to Stanford for his PhD in computer science in the graphics lab. And he worked on stream processing. He has a PhD thesis entitled Stream Computing on Graphics Hardware, and he also developed the Brook software toolchain that was mentioned a few weeks ago when Professor Bill Daly spoke in this class. And the Brook software toolchain is used for abstracting the GPU as a general purpose streaming coprocessor. Currently, Ian Buck is the GPU compute software manager at Nvidia, and he'll be talking to us today about the CUDA technology there. So please welcome Ian Buck.
Thanks. I should mention that Brook was definitely a team effort, although I did get to use it as my thesis. So yeah, I'm going to talk about what we've done in GeForce 8800. That's the latest GPU that has come out of Nvidia, and some of the both architectural features and software stack that we've built on top of it to help leverage people that want to use the GPU not just for graphics or not just for generating images or games, but also leveraging the floating point horsepower for general purpose computing. So I always want to start with what GPUs were originally designed to do. This is some pictures from the launch event for the GeForce 8800. And the important thing to notice here is that the graphics, the world, is evolved extremely rapidly. Every 6 months, NVIDIA tries to double its graphics horsepower. And as a result, the scenes and the complexity of the scenes, the quality, the detail, and just the raw computational horsepower that goes into generating scenes is able to keep up. Graphics artists, game developers, and as well as scientific visualization can pump a lot of data through these chips, and they're always asking for more, which drives this level of innovation and allows us to sort of keep doubling our performance and having a customer waiting on the other end to double the quality, the complexity of the image, the size of the image, the amount of data they process.
What flavor of floating point is this?
This is 32-bit single precision.
Thank you.
So, of course, people have used GPUs for non-graphics reasons, non-rendering purposes. The earliest of that maybe been just straight-up image processing. If I want to filter an image, graphics at its roots is basically image processing, so people have figured out how to do image processing. But it can also be used for signal processing or other areas of data-intensive computation. And the reason for that is that GPUs originated as a sort of a fixed function rendering pipeline. It was sort of geometry in, image out, to a fully programmable platform where geometry comes in and you get to run an arbitrary program on that geometry and images come out. And I'll talk about the graphics pipeline in a minute. But I wanted to give you an example of some of the things that people have figured out even today how to leverage the GPU for general purpose computing. This is a work done by a company called Mercury Computer. They took a collection of our Quadro NVIDIA GPUs and are working on tomosynthesis. So this is basically for mammography, for instance, to cut down on the amount of time it takes to process data. They can actually take multiple scans, X-ray scans, and do 3D reconstruction of the volume data use on the GPUs. And this, because the GPUs have so much floating point horsepower, they can take something that took 5 hours to do offline down to 5 minutes. So taking it from sort of almost real-time sort of results while the patient's waiting, instead of having to come back, make a follow-up appointment, and see their data. Furthermore, this actually, because of this, they could process more data, they could do higher resolution volumes because they had more time to compute, and they could find tumors that maybe they couldn't find in the past. Another example of a company is called Accellaware. They're doing FDTD simulation, which is basically electrodynamic simulation in a medium. And they use this primarily for EM radiation simulation, so cell phone design. When you buy a cell phone from Nokia, Nokia spent a lot of time and a lot of computing horsepower figuring out what should be the shape, design, length, structure of the antenna that's in the cell phone that works effectively, not just in air, but when your hand's grasping the phone, when it's up to your head, and has to talk to a cell tower that may be on the other side of all the stuff that's inside my head. So they actually do these simulations with a real head, with a real hand, to try to figure out what the signal quality is going to be on the other side of my head. Same thing here. This is a picture of a pacemaker. So they do pacemaker antenna design to see what the EM field looks like outside of the pacemaker. So what they do is all this is basically a uniform grid calculation. So it's a blatantly parallel kind of application that happens over a grid domain. And they can parallelize it and move the data from just general CPU processing over to the GPU, and get basically linear speedups as they use more and more GPUs.
The green bar that says 20x is much more than twice the size of the 10x.
It might be an optical illusion. I'm not sure. That's a marketing slide, so there you go. So though there are companies out there that have discovered the ability for GPUs to do general purpose computing, it's not a widespread technology. You don't see everyone today buying GPUs to do computation. There's a couple of reasons for that, and I'll go into those. But what we've done with this next hardware, the GeForce 8800, and with CUDA and the software stack that we've built, is try to make sort of general purpose computing on GPUs a lot more accessible to folks that want to use the GPU for it. So we've added a couple things to the GPU architecture that I'm going to go into, some details, architectural features that make computing with GPUs easier. We've added of course, architecture only gets you so far. We've added a whole software stack on top of this, so that instead of programming in graphics languages and terms and APIs, there's a dedicated computing platform that's targeted toward this new architecture. And of course, marketing slide. There's, basically that gets you to that higher performance, and also potentially opens up the GPU to application areas that it wasn't well suited to before due to the constraints of the architecture. So let's talk about the computing model. If I had to give sort of what the graphics pipeline looks like in one slide, you guys are smart. Maybe you can figure, you can get it from this one slide. But effectively, this hasn't changed. This has been the same way for at least 5, maybe even 10 years. If you go all the way back to the SGI days, you see a similar pipeline developed. The input of the graphics pipeline is generally triangles. You submit the whole world. This room would have to be deconstructed into a base primitive of triangles and issued to the GPU. So the GPU basically receives a whole bunch of triangles that it needs to convert into an image. The triangles, of course, are oriented in 3 space. The pipeline starts with a vertex program. That's basically the program you run on the triangle. So every triangle, you're allowed to run a program that can stretch or translate or move the triangle into its proper position on the screen. So that's a fully, in today's graphics hardware, that's a fully programmable engine. Basically, it receives as input one vertex of a triangle, and the program is responsible for translating that vertex into the world. Yeah?
Can those programs execute branch statements? Or
Yes.
They are, okay.
They're similar in functionality to CPU programs, except they tend to be they're restricted to be a little bit shorter because there's hundreds of millions of triangles to process in a 60th of a second, which is the typical frame time for a render scene. After the vertex program has been processed, the triangles are all in the right place in the world. We now and projected onto the screen. There's a fixed function unit called the rasterizer. All the rasterizer does is take that triangle and transform it into little pixels. So if that triangle covers a portion of the screen, the rasterizer is responsible for generating what we call pixels or fragments for each of those places the triangle covers on the screen. And then there's a second programmable unit called the Fragment Program that basically takes as input a pixel on the screen. You're given the XY location, the triangle data, whatever lighting information is available in the room, and environment information, and you have to produce a color. So this is basically the back end of the process. After we've taken our triangles, transformed them into pixels, we now get to run an arbitrary program to figure out, okay, at this XY location of this triangle with this environment, what the color should be. Typically here you do lighting calculations. Okay, the angle of the surface determines how well it's lit from a particular light. Or you can take decals, or what they're called textures, images, and paste them onto pixels if you have a certain surface with a certain texture, like this shirt or whatever, a pattern. Or compute your own pattern to draw. That, of course, gets dumped to the GPU memory, and that memory is scanned out as part of the video display. Graphics pipeline in 30 seconds or less. How do people use this for general purpose computing? Well, it's quite simple. All the floating point horsepower is sitting basically at the back end of this pixel fragment processor. The reason for that is there's you may have 100,000 triangles, but you're going to have 100 million fragments. So most of the performance is sitting here, which is many more pixels than you do triangles. So a typical GPU program, I should mention GPU stands for General Purpose Computing on Graphics Hardware. It's an acronym that was coined, I guess, at least 4 years ago now, that is defined sort of using, for doing sort of general purpose computing with legacy graphics hardware. Programs usually work by sending down a quad, basically a square. That, of course, is just two triangles that are put side to side. The vertex program doesn't do anything. The rasterizer basically turns that triangle into a bunch of pixels. And those pixels effectively are independent units of computation. They get written to a screen. So if I'm going to add two long vectors, I may send down a rectangle which has the same number of pixels as elements in my vector, read my two values from my two inputs, do the computation, and write it out to the screen. Sort of kind of a primitive array-based programming model. But it's a little elaborate because at first, this is not how these chips were originally designed, right? You have to write an OpenGL program or a DirectX program, or basically these are two main graphics APIs that are available today for doing 3D rendering. And you have to construct these programs. And of course, if you read an OpenGL book or DirectX books, it doesn't tell you how to use GPUs for general purpose computing. It tells you how to light a scene or something like that. This is kind of what one of those fragment programs, from an architectural drawing, sort of an architectural programming model standpoint, what it looks like. It has a set of input registers. Those are predefined by the rasterizer. The rasterizer has decided, okay, this fragment program needs to work on this XY, and here's the triangle data, and such. You have a fragment program, which consists of a sequence of instructions. The assembly is very similar to an x86 assembly, with some constraints. I'll get into that in a second. The input you have one is texture. These are those images, or decals you want to apply to triangles or pixels as they're to determine their color. In a GPU world, in general purpose computing, this is our memory. Basically, we have a whole bunch of memory stored as images on the graphics hardware, and we read from that memory. There's a set of constant registers, which are basically fixed constants and that are cheap and affordable. And of course, some general purpose registers for doing your computation. The result of the fragment program gets written into an output register, and that output register, when the program completes, that whatever's in the output register becomes the color on the screen. So this makes sense from a graphics standpoint. Yeah?
This is a really stupid question. Is there equivalence of L1 and L2 cache on a GPU, or is it just texture and layer?
There are caches in the GPU, but they tend to be designed for graphics needs. For instance, if you notice, this texture is a read-only memory space. So the caches tend to be designed for read-only data, which simplify the caches significantly. So what are some of the problems with using this for general purpose computing? First is, I mentioned this before, you've got to use a graphics API. And there's a lot of overhead into setting up scenes, setting up the lighting consistence, setting up all these sort of, setting up these textures and images but not for what they were going to use for, not for rendering, but for your own purposes. A big overhead. In fact, this is probably the number one thing that stops people when they read about it, they get excited, and then they realize they've got to become experts in OpenGL and experts in DirectX and these advanced APIs just to get to the point of doing the simplest, add two vectors kind of program. Once you get to that point, you run into some other problems. Addressing mode. So accessing memory is done through reading images. And what that means is you have a series of textures or images that are stored in GPU memory. And when you access them as images. So I want to read from image B at position X, Y. If I had to explain this to a regular CPU guy, it would be defining your memory space as a segmented 2D memory space. And we've gone well past segments since, I think, 286 or something like that. The 386 got rid of segments. So it's very confusing. Plus, these images can only be of certain size, typically 4K by 4K elements. It's not a general purpose memory interface. It's a specialized memory interface. But for a lot of problems, you can get around that, but it's confusing. The shader capabilities. Basically, what can this program do? Well, one big thing that's constrained, if you notice, all of your access to memory is through images, but your output is only through these output registers. Your entire program can only write to one memory location, which is, it's like if by that you're designing a program, you're going to write to a region of the screen, and the rasterizer basically decides, okay, I'm sending down this triangle, it's going to cover this portion of the screen. I now have to figure out what the function that sits on top of a particular memory location has to be. It's a very sort of functional programming language approach where you don't get to decide where you want to write. You just have to define the function that sits over a region of memory. Functioning languages are great. They're pure. They're appealing from a theoretical standpoint, but they tend to be pretty constraining when you want to get down to real performance. And how can this makes sense from a graphics standpoint, right? You're writing a triangle to the screen, but from a computing standpoint, it's quite awkward. In fact, this restriction alone tends to be the biggest sort of constraint in the programming model because you have to design your whole algorithm around this functional approach. Instruction sets. Before the GeForce 8800, everything was done floating point. It's sort of backwards to the way architectures were designed in the past. Of you started with integers, and then someone came along and did a floating point library, and then there's floating point hardware. We started from floating point from the get-go. The reason for that is we tend to work in color spaces, which tend to be 0 to 1, that kind of thing. They don't tend to be arbitrary integer values. You also were missing bit ops, so you had no sort of you were missing all the fundamentals of a CPU instruction set. This further got complicated by addressing modes because you had to do all of your addressing in floating point space. So imagine trying to compute addresses into an image or into a memory, and then you realize once you got to a certain size, floating point numbers start to skip integer numbers. So there's certain spaces of your memory you just couldn't address. One other area is that this tends to be very sort of a communication limited architecture. Pixels, or these fragment shaders, are not allowed to talk to their neighbors. Typically, our graphics hardware is actually working on multiple pixels at the same time. It wouldn't make sense to have one extremely fast shader doing one pixel at a time. We'd have to run that at an extreme clock rate in order to get our times down. So what graphics architectures do is they actually stamp out multiple of these fragment processing units to work on multiple pixels in parallel. Well, one thing you notice in writing general purpose programs is that you often, because they can't communicate and because you're only writing to one location, you often have to sort of fetch the same data that your neighbor's probably fetching. Or if you're doing some kind of basic filtering application, you're writing to this location, he's writing to that location, you're often just reading neighboring data and you end up overfetching. And sort of hoping, praying that any caching architecture under there is picking it up. Of course, the caching architecture was originally designed for image processing and designed for rendering, not general purpose processing, so you tend to blow out these caches pretty quickly. So you also get overfetch, and you also get over computation. Some of the addressing math that you would normally do to figure out, okay, where I should read from here is the same addressing math your neighbor is doing. So it's wasteful. And then, of course, I've emphasized the inability to basically scatter. You can't decide where you want to write to. So imagine thinking about how you write some of the core basic algorithms that are available that have been done in the 70s and 60s and 50s, basic sorting, without being able to do an indirect write. Pretty constraining. Actually, it's kind of interesting because it allows you to rethink a whole bunch of algorithms, revisit sorting on this kind of architecture, which that opportunity from a researcher standpoint doesn't come along that too often. So what the architects did was they took the original, GeForce 7800 was the previous chip. They took the fragment processor and they said, okay, what constraints are here that make sense for graphics, but maybe we can relax some of those constraints to make it a little more easier to solve some of these problems for general purpose computing. So you start with the picture again, input registers, output registers, textures, constants, and the fragment program. They added basically three things. One is, okay, let's not call these things fragment programs anymore. You're not operating on pixels. You're not generating images. Really, what you're doing is every little pixel on the screen, every little location that you're trying to write and program that you're running effectively is a different thread. So let's just call them thread programs. And what I'm going to do is actually issue a bunch of thread programs to operate over a set of data. And instead of having my XY location of the screen and triangle data come into these input registers, well, we'll just get a thread number, a thread ID, and the hardware will just dole out, kick off the fragment program with lots of threads, and each thread will get a different thread ID, and we'll use the thread ID to figure out what part of the problem I want to solve. Along the way, they actually improved the fragment program because they realized that having only floating point instructions is a little constraining. So the big features are these programs could be statically 1 million instructions long. There's effectively virtually unlimited every program that I want to run. I should say function effectively that I want to run over a set of data can be up to a few million instructions. There's full bit and interop. So we basically have sort of x86 or CPU parity instruction sets. The only thing missing, I think, is branch indirect. So we can't do function pointers, but pretty close. There are no limits on branching and looping. In the past, in previous GPU architectures, you could only branch so many times, you could only loop so many times before the hardware kicked your program out of the machine. This was due to architectural constraints that were internal. Those have all been alleviated, so you can branch and loop as much as you want.
So it's millions of instructions executed or millions of instructions in your actual program?
In your actual function.
So
you can have multiple. I should say that you can have a function that you want to issue on the GPU.
Yeah.
That function can compile to up to, I think it's 2 million static instructions compiled. Okay. You can run for as long as as long as you want, really. One thing they did do, we noticed that a lot of GPU applications, people using the GPU were often doing things like imaging or volume processing, and we wanted to sort of save on all the addressing math you might have had to do to figure out, okay, this thread ID needs to work on this part of the volume or this part of the 2D image. The hardware actually can dole out not just a 1D thread ID, but a 2D thread ID. So you can kick off 16 by 16 threads in the GPU and get a thread ID that's already pre-segmented into a two-dimensional number. This helps a lot with cutting down on some of the addressing math. One big complaint, obviously, was the inability to scatter. The access to memory was super constrained. So we opened that up. We have a fully general load store to the GPU memory. The memory that's on the board, there are load instructions or store instructions. There's no restrictions on how you can access it. It's really just like a CPU here. This was an obvious one. It causes a lot of sort of interesting dilemmas. If I have multiple threads hitting the same location, it's just as if I had multiple threads in a CPU hitting the same location. There could be race conditions and that, but we've opened it up. So as a result, it's really up to you to decide, okay, I can kick off this many threads and decide how you want to partition your data across the problem. Previously, sort of basically the data partition, the data parallelism defined how you wanted to parallelize your problem. Now you can decide how many threads make sense and then to access what region of my one big emphasis is this is all untyped memory. But in the past, those images, those textures were all type defined. You had to create a RGBA image, and each channel had a float, a 32-bit float or a 16-bit integer. It was very confusing, and it didn't make sense in a general architecture to try to make all memory typed because people create structs and all sorts of things. So it's fully untyped memory. Of course, with the access to global memory, we can do full pointer support in our programming model. So we can do, which we didn't have before. The only access to memory was through image referencing, but now we have full pointers and that sort of thing. These things, I mean, from a CPU standpoint, seem obvious, but to have a GPU to do this was a big deal. Okay, so we have threading, we have access to memory. The other big one that we were missing was communication and cutting down on allowing threads to intercommunicate with each other, and also try to cut down on the number of times we had to go to memory. So they added this piece of hardware called the parallel data cache. This is a dedicated on-chip memory that's shared between all the threads that are resident in the machine. So you can think of this as, in effect, a software-managed cache where you can allocate variables that live in this parallel data cache. It's not a hardware cache. You have full control over what gets allocated, when you access it, and that sort of thing. And you can block your computation for this cache. So it's because it's on chip, it's very fast, and it's shared across all the threads, so the threads can intercommunicate and cooperate. I'll give an example of that in a second. But I want to emphasize that it's explicitly managed instead of hardware managed like a CPU L1 or L2 cache. Yeah?
How big is this cache?
It's 16K. So here's a sort of basic example. If I'm doing a fluid simulation, I'm at the pressure stage, and I need to, it's an uncompressible fluid, so I need to normalize the pressure across the entire grid. I'm doing a finite, there's people in the audience who know this math better than I do, so I'm not even going to use the words. But if I had to boil it down to a simple thing, you're just updating the pressure, and you're doing an iterative solve, a loop over the grid to figure out to resolve any pressure indifferences because it's an incompressible fluid. So the pressure to update, you look at your neighbors, see what the pressure is of your neighbors, and update your pressure value based on that. And typically, so in a legacy GPGPU application, I may be sending down a rectangle that covers the entire grid. For every grid point, I look at my neighbors and compare and update my pressure. Of course, neighboring values are going to be reading the same values, and you have the overfetch problem. Plus, this is an iterative solve, where I maybe need to do this multiple times. But every pass in a legacy GPU application, I've got to write it back out to memory and do a whole other pass over the grid again to update the pressure. So I have to always loop through off-chip memory. So on the left, I've got the CPU version. Effectively, it's you can work out of a L1 cache, but you typically have very small ALU. In traditional streaming GPGPU, you sort of stream all the stuff through the video memory. So your pressures, like I described, every time step of the pressure, every iteration of the pressure solve, you're looping through GPU memory. This can quickly make you GPU memory bandwidth or pin bandwidth limited. With the parallel data cache, you can basically put the pressure field in that shared memory that's shared between all the threads. So I can load a region of my grid into the shared memory. I save myself on the overfetch because I've only read it from the video memory into the GPU once. I have full control over that, so I know I'm getting good caching. The other thing I can do is I can spin on this memory and do the pressure solve. I can do multiple iterations in the parallel data cache instead of having to go all the way out to video memory. And as a result, my problem switches from being a bandwidth limited application to being an ALU limited application, which is the higher performance aspect. So this, I've talked to this already, but it basically addresses one of the fundamental problems with legacy stream computing. Is that stream computing, by adding a parallel data cache, by adding an on-chip sort of indexable memory, I bring the data closer to the ALU. And I'm sure you guys have had architecture discussions already in this course that highlighted different architectures that leverage this. Yeah.
What is the parallel data cache size?
It's 16K per processor. So I'll talk about what the 8800 looks like in a second. So just to highlight it, streaming typically is a gather in. So legacy GPU on previous architectures, it was characterized as streaming, where you did a gather in, reading from images at any location with a restricted write, and the memory tends to be far from the ALU with no inter-element communication. With CUDA and the 8800, there's a more general data parallel model, full gather scatter. It's up to you how you want to parallelize your data, parallelize your computation across a set of data. And you're allowed to communicate and solve problems more efficiently. So this is what we've built. So that's the general architecture of what's new in GPUs to help. This is the first implementation of this is in the 8800 GTX. Just some data here. The core clock on this is running at 575 megahertz. It has 128 multiprocessors. Basically, what that means is there's 128 ALU engines we can do in the chip. Those ALUs are running at 1.35 gigahertz. So most of the chip runs at 575 megahertz. The ALUs run at 1.35. The memory is 900 megahertz, and this card that you can buy this at Fry's today has about 768 megabytes of memory. Yeah.
So do each of those ALUs have 16 kilobytes of parallel cache?
Here's the block diagram. What a G80 looks like. 8800 looks like internally. So what there is there's a command stream. We kick off functions on the GPU. We say we want to run this many threads in this configuration. Those collections of threads are doled out to the different processors. And in the 8800, actually, there's 16 thread processors. Each thread processor has, what is it there? 8 ALUs per, and then they all share a parallel data cache. So we have multiple, basically, processors in the machine that are working on the threads in parallel.
Leon, on the last slide, was it 900 megahertz pin bandwidth, or was that clock rate for the DDRs?
That's the clock rate for the DDR.
Okay, so it's twice that. Okay.
Well, no, so it's divided by 2. This is taking the DDR times 2 number.
Okay.
If I look at the clock, DDR both edges.
Is that the data rate or the control rate is the better question?
The data rate is, we get about 60, we see observed 60 gigabytes a second of bandwidth. So each thread processor, yeah, I've already talked to this, 16K, there's your number. One thing I should emphasize is that it's a fully scalar architecture. So in the past, GPUs have been all vector typed. It made sense from a graphics standpoint. You're working in colors. They tend to be RGB, maybe an alpha, or an XYZ and a W homogeneous coordinate. So it made sense to be a vector architecture. This was a kind of a pain from a general purpose computing standpoint because you had to take all your programs and try to do them in a SIMD kind of fashion. The architecture is natively a scalar architecture, so there's no performance benefit necessarily to using the vector types, although they're still there if you want to from a programming model. Precision is a question we get a lot. Basically, it's IEEE single precision floating point that you get on a CPU with some exceptions. We don't have D-norms, so we will round to 0. But the rounding mode, we support all the different rounding modes, and the default rounding mode is round to nearest even, like you would expect on a CPU. But it is single precision. And I've talked about the feature set. Basically, it's effectively very similar to a CPU instruction set, with the exception of, branch indirect. So that's the architecture. But I'm actually the software manager, so I was given the task of given this architecture, can we build a software stack on top of this to help people target this architecture? Because one of the biggest problems was, people didn't want to use OpenGL or DirectX to program this thing. They wanted to use a more familiar platform. So the first question is, how do we talk about the GPU? Well, in the past, GPUs have often been referred to as sort of a graphics device. There was often an API, and you were controlling the API like you were controlling any sort of external peripheral in the system. from a computing standpoint, that doesn't make much sense. You don't want to think about a computing machine over there that you have to talk through, like a networking thing. Really what we want to do is expose the GPU more as sort of a highly multi-threaded coprocessor. So it really should be sort of a coprocessor to the CPU. But it has some peculiarities. It has its own DRAM memory, so we need to have a separate memory space. And it also runs many threads in parallel. So it's not really a CPU. It's a slightly different architecture. But the idea here being is that we can take our application and take the sort of the data parallel portions of our code and offload them to the GPU to accelerate them. I want to emphasize that even though we're talking about threads, threads have a sort of a bad rap on the CPU world, that they're very heavyweight. They're heavyweight to start. They're heavyweight to switch between. You typically take an OS interrupt, and all this OS has to get involved. On the GPU, we've designed the whole thing is designed to be multi-threaded from the get-go. So switching from one thread to another thread happens on a per clock change. So they're very lightweight. They're lightweight to create, and they're lightweight to switch between. As a result, we can have lots of them in the machine and keep the machine busy because the machine is very efficient. If it has problems or has to hide latency with one thread, it can quickly switch to another thread and fill that latency. Oh, I should emphasize one flip thing is that we need lots of threads to keep the machine busy. Typically, graphics is working on screen resolutions, and we have lots of pixels flying and fragments flying, vertices flying through this machine. So natively, we need lots of threads in the machine. So and the big difference between CPUs and GPUs, on a CPU, we may only need 2 or 4 threads to keep all the cores busy. On a GPU, we may, as I showed in the diagram here, we're going to need lots of threads to keep the machine busy. So we often typically work in terms of thousands of threads active in the machine. So the programming model, we could where to start with building a new tool chain, new software stack for programming a GPU. Well, the most logical place was, since we are so close to a CPU instruction set at this point, and so many of our people that want to use this are familiar with C, well, let's just build a C tool chain that works in the GPU. That's effectively what we've done. Now, of course, it's not a CPU, so we can't take all of C, but we did. So we added extensions where necessary, but the general goal was to provide full C support with some extensions. And those extensions are basically keywords that we put in front of declarations or instead of functions. And what those map to, they're defined, they have global here, which is a keyword that means that this function is a global function that should be executed on the GPU. So our toolchain takes that function and compiles it for the GPU. Likewise, this variable, the global var, it has a device keyword in front, meaning that that variable should reside in the GPU memory. Shared means that the shared variable is shared across the threads. It should reside in the parallel data cache. Yeah?
C or C++?
So we're working towards C++ support. Today, we only promise support for C. Our front end is a full C and C++ front end. So all these keywords I've shown here are actually just decal specs or GCC attributes, and our front end can recognize those. The only place where we cheated and extended the language a little bit was to add this sort of funky angle bracket syntax. This is a function call that ends up on the GPU. But to call that function, we need to specify how many threads we want to kick off on the GPU. In fact, you need to specify 2 things. One is the number of threads I want to kick off on the GPU, and what's the collection of threads that get to share that parallel data cache. So we typically express this with 2 numbers. We may kick off 500 threads, and a collection of 500 threads, 128 blocks of threads, each block containing 500. The 500 threads share the parallel data cache. Another area that we're addressing is memory management. We have this GPU memory. We want to provide access to allocate memory and free memory, so we've done that, and it's all explicit. In the past, graphics APIs tend to try to virtualize the memory on the GPU. They treat it as a cache. So you declare your textures and your images, and the driver would dynamically try to download and use the GPU memory as a cache. A lot of complaints from the GPU community, people have done this in the past, and that they are often fighting the texture manager, the image manager, that driver, because it's designed for graphics. So what we've built instead is a runtime API that allows you to do explicit memory allocation on GPU. When you do an allocation on GPU, it returns you a GPU pointer. That pointer you can pass to a GPU function. It can dereference it like you would normally expect on in C. The software toolchain, of course, it's called CUDA, and all these functions are prefaced with CUDA, but they're really just not much different than the C runtime. Yeah?
Do standard debugging tools like GDB and 12
I'll talk about toolchain in a minute. We, of course, also provide memcopy routines to copy data from CPU memory into GPU memory, and, of course, GPU to GPU and GPU to CPU. These all, of course, use the GPU's native DMA engine to copy data back and forth.
You copy memory in between the local stores?
So the memories, these memcopy routines are really for downloading to the GPU global memory, the onboard memory. The on-chip memory is initialized by the program and erased when the program leaves the GPU. So that when this function executes on the GPU, the on-chip memory is effectively is blank, and you populate it in the program. When the function returns, that memory is effectively freed and available for the next function.
As well as running, can you copy between the local memories?
No, so the collection of threads that share the on-chip memory are resident in the machine at the same time, but they're not allowed to communicate with others. So we still restrict you on that sort of thread block granularity. That is still a restriction. The reason for that is we don't guarantee which order the collections of threads are issued are in the machine at any one time, because may add more or fewer processors, or just execute them potentially out of order. So we still try to make the architecture scalable in that sense. So the 8800 had 16 processors. We could build a chip that has 32 or 64, and if your program, as long as you issue functions with enough threads, we'll keep the machine busy. I should also emphasize that a lot of people want to use, the graphics processor is still there. It still can render stuff. In fact, one of the biggest uses, offloading parts of your computation, or parts of your graphics program, like scientific visualization, onto the GPU, and then because it's there, you can use it to render. So we do provide interoperability with OpenGL and D3D. It basically, you can take a D3D buffer object, if any of you are familiar with this, and with CUDA, you can ask for a pointer to that buffer object. It returns you a GPU pointer. You can write and read to it, hand the pointer and the buffer object back to OpenGL, and use it to render. A simple case of this is a particle system. If I have a particle system, a shower of sparks, or a waterfall, for instance, simulations are often done with particle systems. I can do all the physics of the water and physics of the sparks, or attraction, or repulsion, whatever, or collision, using CUDA, and then data's already there. I can use that to then render with OpenGL or D3D. This is an idea of what our SDK looks like. We've built two standard libraries to help kickstart this. A lot of users, we found that a lot of people are interested in FFTs, and we're actually pretty good at doing FFTs. I'll give you some performance numbers soon. Obviously, a lot of people are interested in linear algebra and Blas, so we did a Blas library. Not everything. I'll talk about what's there and what's not there. So these libraries are just standard libraries. You can link them, use them, as long as they're an 8800 in your system, you'll get acceleration. The rest of the tool chain is for, of course, writing regular C code. So you can write your C code. It can be integrated, so portions of your code, as long as you specify those certain keywords, will compile for the GPU. The rest of the code is untouched by the compiler and is handed off to the host compiler. So the front end of our compiler, NVCC, takes this integrated CPU, GPU code. It takes the CPU portions of your code and leaves them alone. Basically, hands them off to whatever host compiler you have on the system, whether that be Microsoft's Visual Studio or GCC or whatever. The GPU parts are what interest us. We run those through our own compiler, which outputs an assembly format. This is basically our instruction set for the GPU, and then that binary is linked in with the application, and there's a runtime library that you need to link with your application, of course, to implement things like malloc and free and whatnot. We also do have a profiler. that can tell you how long a particular function took to run on the GPU, how long the memcopy took, what kind of bandwidth you're seeing, as well as if you hit any perf issues or bad read or write patterns that may degrade performance. I should also emphasize that you don't need to take your entire application and use our compiler. Typically what people do is they have a very large application, they take that one C file that does a lot of the heavy lifting and port that, and then the output of this is just a .o or an OBJ file that you can link in with your application. So it's designed to work in a large program environment. So I should talk about the Blas library. It's a self-contained Blas library. You need no interaction with the CUDA driver. You don't need to learn our language semantics. It's an API, just like it prevents. We actually work with Fortran bindings, that sort of thing. We only did a subset of Blas. Basically, we did single real routines for Blas 1, 2, and 3. We did Blas 1 complex because it was easy, and CGEM, which some people use. We'll add more if customers are interested. It's pretty simple to use. You create matrices and vector objects. It's slightly different than we did have to extend a little bit because we're not working in the same memory address space as the CPU. So allocating of the arrays of the matrices and vectors is done a little differently than a legacy Blas library. But after that, it's just basically called a sequence of Blas, a CU Blas functions. We did all sort of the things we could do to keep consistency with existing Fortran applications. And we have linked this library with Fortran apps, and that all seems to work. Our FFT library, if any of you have used FFTW, it's largely based off the FFTW interface. It's not much different. It features sort of 1D, 2D, 3D FFTs of complex values, signaling data. You can also do batched execution. So if you have a batch of 1D transforms, you can hand off the whole batch, and we'll issue that in parallel. That helps keep the machine full. And we have arbitrary transform sizes from 2 to 16K, and all the different mixed radix kind of stuff in between. And in case anyone's never seen a 2D Spectra, that's what it looks like. Oh, actually, we've ported this. We've actually that pressure example I gave before. We actually used the FFT library to do the pressure solve in frequency space. For mathematicians out there, the frequency space actually is a little more amenable to doing the convolution portion of the pressure solve, because convolution turns into multiplies. So I have a little video of that. See if I can fire that up. So this is run, I think it's a 1K by 1K grid on an 8800. So the little mouse here, then all the particles basically show the flow through the field. So we're doing all the pressure solve using the FFT library. And then we just switched to Core 2 Intel to show sort of the speed up performance. Yeah, this is all real time. This is captured with a frame grabber off the video. So you can see the mouse there. He's moving the mouse around, controlling a jet and playing with the fluids.
What resolution? How many iterations per pixel?
So this is a 1K by 1K fluid solve. The pressure solve it takes it from an iterative to a sort of a one pass in frequency space. The paper, I'll let this finish one more time. I have a paper credit in there. You can. It's very fun. Actually, you can watch this whole thing stabilize, and it turns into one large translation with 2 vortices, and then the vortices stop, and it just turns into a translation. It's pretty trippy.
Is that the same program running on the Intel with the same?
Yeah. So we just hit a button and move the data from the GPU to the CPU, and just do the iteration. Do the same. We're using FFTW, I believe. Same code, same algorithm, using an FFT library on the CPU.
More or less power than a lava lamp.
Probably the same.
Is it running on a single GPU, or are you running on multiple GPUs?
This is one GPU.
So is the OpenGL and DirectX libraries sort of built on top of CUDA, or is CUDA both all written on top of one other sort of more
So that was an option we faced at the very beginning. We could sort of build our GPU library on top of OpenGL or D3D, and we decided, what people really want is a close, a high-performance sort of lean mean driver. So we actually wrote a separate driver from so it's a peer to OpenGL or D3D. This is actually using the OpenGL interoperability I talked about, where the fluid solve is done, we update the particles all with CUDA, and then the particles are again just rendered in OpenGL.
Something underneath because they're sharing the same.
Yes, so the kernel component.
Yeah,
The kernel component, which does the memory management, is of course shared because when we do a memory allocation, I don't want to step on top of OpenGL's memory management. But only the core kernel component, which is doing the scheduling between OpenGL, CUDA, and D3D is
So are there any capabilities then that are open to the OpenGL or DirectX that aren't exposed through CUDA?
So I guess I'd say that OpenGL kind of runs in graphics mode, and when you're running CUDA, it runs in compute mode. So graphics, of course, has things like the rasterizer, which are just not exposed in CUDA. So if you can use the rasterizer for your needs and for general purpose computing, more power to you. But most of the performance is sitting in that fragment shader anyway. So
How well do the two worlds coexist? If you have
the hardware will schedule. We'll do hardware scheduling. So if OpenGL is running for a while and it gets a time slice of the GPU, and then CUDA will run for a while, and we'll schedule it like we do, like an OS would normally schedule a CPU. Yeah.
When you're in compute mode, do you have access to the interpolation units at all, or do you basically only have load store?
You don't have access to the interpolation units. What we found is that actually it's really not that much math to do a quick multiply add, which is just one instruction. So that is maybe a downside to using CUDA, because all you get as input is a thread ID, but it wasn't that much math, so not a huge loss. Go back to the presentation. Oh, crap. We don't have time. Okay. Sorry. So, marketing bar graph, forgive me, but these are actually, oh, sorry. Stop that. Marketing bar graph, but these are observed numbers of some of, basically comparing against a 2.66 Core 2 Duo using both cores. We were careful that on the CPU we should use both cores. Of some performance advantage. In general, we like to see over 10x. A lot of our applications do. In some cases, we get extreme speedups, and I'll talk about why that is in a second. But we did a bunch of different applications. This rigid body solver, again, is, I should emphasize for this crowd, this is a rigid body solver that's used in games, not necessarily in robust scientific simulations. These are some Blas results. Wave equation, this is the FDTD result. Biological sequence match, this is basically looking for loose matching, for protein matching. It's an important benchmark in the bioinformatics. And then finance, this is option pricing, Black-Scholes benchmarks. So here's some hard numbers. BLAS1 is a vector-vector series of operations. Tend to be memory bandwidth just because you're just streaming over vectors. We typically see 60 plus gigabytes a second of memory bandwidth to the GPU. BLAS3 tends to be more compute intensive, right? You're doing ON cubed operations over ON data potentially. And that gets over, we see typically over 100 gigaflops of sort of BLAS3 library performance. FFT, if you take, there's a benchmark, there's a website FFTW actually uses called Bench FFT. They provide a numerical formula for computing how long an FFT should take of a certain size and how many gigaflops that theoretically corresponds to. So I say it's using the Bench FFT equation, we typically see about 52 gigaflops worth of performance for FFTs. FDTD is the electromagnetic simulation I talked about at the very beginning. And we can update 1.2 gigacells per second. SSearch is the protein matching, sort of string searching algorithm. 5.2. And then Black-Scholes option pricing is ridiculous, 4.7 gigops options per second. So why are these numbers so great? I should emphasize, of course, we have more memory bandwidth than a typical CPU because graphics tends to be very sensitive to memory bandwidth performance, so we use the fastest memories and dedicate a lot of our pins to memory. But importantly, we can leverage that parallel data cache. So we can capture some of the gigaflop performance, all those shaders that are in the GPU, by keeping the data close to the ALUs by spinning inside the parallel data cache instead of streaming out to video memory and back. GPUs tend to have a lot more gigaflops than CPUs in terms of raw gigaflop power. And some of the reasons why we're seeing 197x is because some of these benchmarks can take advantage of hardware intrinsic instructions. For instance, graphics has a dedicated sine instruction, cosine instruction, that executes only in a few cycles, instead of the math.h sort of sine instruction. Now, of course, they're not full precision. They're enough precision that matters for graphics, but for something like options pricing, you can sometimes just get away with a lower precision and much faster results. I should also emphasize that all the benchmarks are compiled code. There's, my group, we don't hand code anything. We try to use our own tool chain and evaluate that as part of your performance. So to conclude, I guess I'm getting close on time. I've talked about GPU computing on the 8800. We've basically added a simple multi-threading model to the GPUs with a parallel data cache and global memory access. The software tool chain basically is C on GPUs with a couple of extensions for dealing with the fact that you have lots of threads in the machine, but it's effectively C. Our front end is a fully licensed C and C++ front end, so we're fully compatible, even bug compatible with GCC and Microsoft. The toolchain, the driver, is all dedicated for this. We're not doing this on top of OpenGL or D3D. We've built our own custom driver to give you direct access to the hardware. We've done 2 libraries to help you sort of kickstart. If you're just interested in FFT, you can start using these right away. And availability, right now we're in a beta program. This is basically it's early software. There might be some bugs, so we're doing a registered beta program to help people that want to try out new software and give it a shot, maybe, and help us figure out some of these bugs. They can register online, and as long as you fill out the form and don't say you're Mickey Mouse or something like that, we'll accept you, and you can try it out. This should work on any GeForce 8800 that you buy at Fry's or elsewhere. We're trying to work toward a public release early next year. One question I often get asked is single precision, double precision. I'm not interested because I don't have double precision. We are planning to do a double precision GPU next year. So that is, double precision is coming and is on the roadmap. Full IEEE works. Maybe not signaling NANDs, but that's okay.
This will not work on older GPUs at all?
This is just for the 8800 and onward. So the solution will be forward compatible. It's not just a one-off.
Can you run?
Let's start and we'll move it back. Yeah.
What did you discover you wished you had in the hardware when all it doesn't settle?
There's a lot of stuff we've learned as doing this. Double precision was clearly one of them, and something we didn't get right away. It's difficult to explain without going into details of teaching it. One, I think we can improve access to memory even further. We're working in a big parallel environment, so we need more sort of atomic parallel intrinsics to help us deal with the fact that we have lots of threads in the machine, and we maybe need to update things more atomically. I think we're working on that and trying to improve that as well.
Yeah, so one of the questions, is there any utilities to mutual exclusion?
So we do have a synchronization primitive. I didn't get too far into language in this talk, but one thing is that you have this shared memory that's on chip, so you can do a parallel load across all the threads to bring stuff from video memory into that on-chip shared memory. And there's a synchronization barrier primitive that you can place in your code, and that's basically a barrier in the code to make sure everyone's done their loads before you work on that parallel data.
How many programs can you populate reasonably to get I mean, you have thousands of threads, but you can't. I assume you can't have thousands of programs.
No, typically what people do is it's not strictly data parallel in the sense that you don't run one thread per data element, but you typically run one thread for a collection, or some case in one data element.
So environment rather than just a single program, couple.
Yeah, so usually you kick off a function over an entire grid, and that corresponds to your grid of threads. I think you were next.
How well does this scale with respect to having multiple 8800s on the same motherboard?
So our goal is to provide, so you can put, motherboards today I think have 2 PCIe slots. I think we just announced a 3 PCIe slot solution. We also have a product called Quadruplex, which is a breakout box. It's an interface card that plops into a PCIe slot. It goes to an external chassis with an external power supply that breaks out into 2 PCI slots. So this can grow. I think I don't want to say how many we can do right now because I'm not sure what the final number will be. But the program model is meant to be explicit. So we're not trying to auto-parallelize across the different GPUs. You can ask how many GPUs in the system, connect to that GPU, use that GPU. You can run a different thread or a different program on a different GPU or the same, or do the data parallels, data decomposition.
You can run the one program on multiple GPUs.
Sure. In the back.
So maybe I misunderstood or missed this. So when you create these threads, they're issued this thread identifier, and you use that to figure out what data that you as a thread are working on. So
right.
you do those computations internally in the function itself, or there are some other, or that they just work on a set of data and a set addresses, and you spray out the data ahead of time in the way that you want.
Right. It's totally up to you. All we're giving you is a thread ID. It's totally up to you to decide how to do the point arithmetic to decide what thread wants to work on that piece of data. We're not going to spray the data around for you dynamically. We thought about that, and conceptually that's possible. But data decomposition in a parallel programming environment, there's PhD theses and different ways of doing that for different, for structured meshes or regular grids. And it's something that it's clear you want to program. You want the programmer to decide how they want to decompose their problem and decompose their data set to be efficient. So we don't do any sort of dynamic, this thread must work on this region of the data. You just basically get a pointer, and you typically take that pointer and add the thread ID to it.
You take the thread ID and decide what data
Correct.
I have 2 questions. So first, is the language that CG compiles to open standard? Is it published, or is there some black box that we don't know?
So this is not CG. CG is a different language entirely. This is all C. So we've done. There's a shading language that Nvidia has developed for doing sort of graphics shading called CG, and that's used for. And it has things like texture, and it's the legacy path. This is all just C. It's a totally new compiled shade.
Is the stuff that you compile to is assembly language that is compiled to open standard, or?
It is published. It's standard in the fact that Nvidia designed it. It's designed for our architecture.
And how does this compare to ATI CTM stuff?
I think the biggest difference between CTM, there's a couple things. CTM does have gather scatter capabilities or access to memory. They don't have the on-chip memory that the 8800 has, the parallel data cache, which is a significant sort of, you still have sort of, your program still sort of stream through memory. The other thing is that our language solution is we have a much stronger effort on a software tool chain. CTM is a ISA spec that you can, and you have to still use sort of legacy shader languages to compile to that ISA and maybe tweak them. Over there.
How much power?
Yes. Don't know the exact number off the top of my head. I think peak is around 100 watts or something like that. Maybe more. It can get hot, yeah. But there's power to spare these days in a chassis. It's enough to cool it.
Yeah. So I'm trying to look forward a bit. Is this sort of the point where GPU designers really start thinking about compute needs and designing their chips for that? Or is it mainly still we do the graphics first and you can get this little bolt on here and you're secretly hoping that we all go blind tomorrow so that you can get the hardware designer's real attention here? I mean, how do you see this developing from here on?
There is a trade-off between the graphics programming model and the compute programming model. What they basically just tried to do is design a computing programming model that is sufficiently general but still within the right direction that scales, so graphics can continue to scale and add features that are aligned with the way compute wants to go. One important aspect is that if you look at what GPU has, the trend historically is they've always been sort of one step up above, ahead of what graphics shaders want to do. GPU programs tend to be much longer, for instance, than graphics shaders. They tended to want to use integers and bit ops than before graphics did. But as you see, features that were requested in GPU becoming regular in graphics. So it's one of the driving things in NVIDIA in general in designing of GPUs is making them more general purpose. Because if you look at what the shaders are trying to do today, they really are becoming way more general purpose in sort of solving complex lighting simulations, doing some primitive ray tracing to do global illumination, that sort of thing. So it's an effort to make GPUs more general purpose because that's sort of the directions graphics shaders are going. So we're aligned in that sense, in that we're both pushing in the same direction. They still want to render an image when they're done. But it isn't to say that you could do part of your game physics with the GPU, and definitely game physics is a very interesting area for NVIDIA because it's more horsepower in the GPU, meaning your game could have more objects, more simulated physics objects in your game than you could before because they were CPU limited. Let me start over here. Is that in this corner?
More on synchronization primitives. You said you had barrier sync, but that's pretty heavyweight for lots of programs.
Yeah, I should say that it's barrier within a collection of threads that are sharing the parallel data cache, typically 100 threads within a function. The machine obviously may be working on multiple collections of those threads in parallel, so it will keep the machine busy. And the barriers are hardware accelerated, so they issue very quickly if everyone is in the same place in the code.
Producer-consumer kinds of things between threads, much.
Yeah, we typically don't do much producer-consumer. We need so many threads. Producer-consumer, you can think of it as a form of task parallelism. You have a producer and you have a consumer. Typically, we fill the machine with so many threads that we tend to follow more in the data parallel camp than a task parallel environment. We can talk more about it afterward. Back.
You mentioned 16K for the data cache, but what's the size of programs you can fit on for the threads?
The threads can be up to a few million compiled instructions per function.
But there's not storage right there for that.
Yeah, no, the programs are stored in the GPU memory, and there's an instruction cache that you don't have to worry about and all that kind of stuff. So unlike I think Cell, there's a limited. You have to use this on-chip memory for instruction store, so your programs have to fit in the 256K, and none of that's there, so that's fine. Yeah.
You expose the texture units for the API at all?
Yeah, the texture stuff is all still there. So a lot of people have figured out that texturing, the image fetch engine did a lot of useful things. Like it did filtering between two pixels in an image. It also dealt with boundary conditions, so it could do clamp to edge or mirroring modes. And a lot of people figured out that was very useful for general purpose computing because they could take their boundary condition and just throw it to the texture unit and not worry about it. All that's still available to you, and you can take any GPU piece of memory and bind it to the texture and access it through the legacy XY sort of position stuff. Yeah.
So the GPU kernels execute only on GPU memory, and the programmer has to explicitly copy data between CPU and GPU?
Yes. The bulk of the data resides in GPU memory. You need to memcopy it down or memcopy it back to the CPU. We do allow parameter passing, so when you call a function on GPU, you can pass, we have parameter space, and you pass things through parameter, although you wouldn't pass an entire data set that way, obviously. You may pass a GPU pointer or a value, that sort of thing. How much time do I have?
We have about 5 more minutes, and we can go about a couple to 5 minutes over.
Well, I'm around afterwards, so let me see if anyone else.
A lot of scientists like Max. Is there any chance of seeing this on Apple as well?
I would love to get this ported onto Apple. It's just it's a matter of manpower.
How do you see it going as far as going up to high performance computing? You know, sort of a bunch of these on one rack, and then down on the other end, sort of to play in the DSP market. I don't know if you're going to plan an 8200 version of this.
Right.
That gets maybe a little bit less than 100 watts.
Yeah. So this will be available on the entire GeForce 8XXX family, including the lower end part. So right now we have the 8800, but it's typical NVIDIA does provide, you know, a variety of different products at different sort of price, performance, power spots. So this should be available in all those.
Specifically in a DSP market, do you see this playing?
Potentially. I mean, basically anywhere where the, you know, DSPs or, you know, cell phones, they want to do video processing, they want to do image processing. We tend to be pretty good at that. Right now the emphasis is on the GeForce line. We don't have any products for the DSP market, but yeah.
That pressure simulation, that was 1K by 1K.
Yeah.
It's a big number.
Sure.
How did you fit that into the GeForce memory?
It fit within 768 megs. So
Work that out for me. You've got 16 processing blocks, each with 16K of memory.
No. The memory, the pressure data resides in the GPU memory. It resides in 768 megs. The FFT is done is blocked for that on-chip memory explicitly. So the whole data set doesn't need to live in the 16K. We actually we block the computation for that on-chip memory, like you would block, for instance, on an L1 or L2 cache on a CPU.
Thank you.
You had a question?
Yeah, it looks like this chip is not going to show up in the one laptop per child at 2 watts.
Not right now. In the corner?
What's a thread context look like?
Sorry?
A thread context.
A thread context. So each thread, when it kicks off, gets a thread ID. It is the parallel data cache, that shared memory, is initialized, is uninitialized. It's empty. We have a program counter. There's access to some texture, so you can access the images if you want to. There's constants, and of course there's registers. So it's fairly similar to a x86 architecture, except that you have lots of threads in the machine at the same time, and we've added some extra memory spaces.
And the stack is then shared?
Oh, I didn't mention that there is a per thread local address space as well that you can use for stack or indexable memory in a per thread space. Yeah?
Can you step through thread programs?
We don't have so our debugger solution right now, because we're so close to C, we can basically give a flag to NVCC and it retargets and will compile your code basically back to the CPU. So and then our runtime library runs in a sort of GPU emulation mode, where instead of kicking off 100 threads on the GPU, it kicks off 100 threads on the CPU, and you can use your regular CPU debugger, VisualStudio, GDB. We actually relax a lot of the constraints, so you can go ahead and put printfs in there and that kind of stuff to do printf debugging if that's what your preference.
So typically, I think, don't GPUs typically have performance counters? Does the profiler give you access to that?
Yeah, it does. So it'll tell you when you do. There's some. I didn't get into some performance details. There are certain write patterns that like on CPUs that are more efficient than other ones, and our profiler does give you not just timing information, but how many times you may have made one of those misaligned writes, that sort of stuff, or how many times you issued a branch, that kind of usual performance counter kind of stuff.
So you refer to the memory as a cache. So it's really just a memory that is used.
Yeah, it's just a memory.
There's no cache.
Well, it's software. Yeah, effectively, we call it a cache because it's really close to the LUs and people are used to but it's really a software managed cache in that regard. So it's not. There's no hardware mechanisms to deal with tagging or any of that sort of stuff.
But even in software, there's no replacement policy.
Correct.
It's really just a memory
It's
that
just
the user
a memory. Yeah.
manages. And And do you provide any function for moving primitives for moving data and doing double buffering and all these?
No, it's just load store. So you reference a pointer and store it in a variable, and that variable is declared as shared, and that means that shared gets put in that parallel data cache. So it's just a regular copy.
Data from the kernel memory to the on-chip memory.
Correct.
You have it. Oh, you just do.
You just do load store like you would see. Yeah.
You compared your performance to CPUs. Could you talk about things like cell compared to GPUs? And
I don't have any good performance numbers with cell. Probably because we don't benchmark the same things. I can talk a little bit about GPU before and after. I mean, that parallel data cache does help you a lot. For instance, the FFT, before we had to do all that, an FFT calculation had to go all the way throughout to video memory and back, and was extremely expensive and slow. We were getting something. The parallel data cache is giving us like a 10x kind of improvement by using this. This picture, yeah.
When you pump data from the video memory into the local stores,
yeah,
and you want to get maximum throughput, is there any sort of tricks you have to do? Because I mean, I'm just, especially if you just say it's just load store, no prefetching, or how does it? Because all you're doing is loading up 32-bit registers.
Sure.
It seems like you're not going to drive the memory fast enough.
Right. So typically, the reason why you have so many threads in the machine is that we can often hide the latency of off-chip memory read, like a read from the GPU memory, by scheduling in another thread. So you can keep the memory busy by having lots of threads accessing memory. And
what about the width of the data access?
You can get almost full performance with a regular 32-byte load.
32-byte?
So I should emphasize you have multiple threads accessing 32 bits. I'm sorry. 32, just a regular word access. But what's happening in the machine is you have parallel threads executing at the same time. So you're actually having multiple word reads, and the memory controllers are keeping the DRAMs busy by servicing all those loads in stores. Yeah.
So you sort of draw the parallel data cache off of the side. Does that mean there's a performance penalty when you use it versus your own registers?
Or is
it just the same as registers?
It's pretty much the same as registers.
So then, you're running in GPU mode. Is that just wasted, or?
It's used for other things.
Okay.
It's used for rendering stuff. Yeah.
What are the next versions of the GeForce going to be scaling? Like, is it more of that parallel data memory, or more ALUs, or?
Yeah, I mean, the architecture. Yeah, the programming model and the architecture is designed to be scalable, so that we could support more parallel data cache. We also could put down more of these processors if we have the desire to do so.
What's your priority to what to scale first? Since you're going to be targeting graphics first.
Oh, I want to scale all of it, I think. Definitely having more on-chip memory is a good thing. I can block more. Usually means I can get more performance. There's plenty of algorithms that get better.
Like texture memory as opposed to parallel data memory?
Yeah, that parallel data cache, that on-chip memory. Texture is generally off-chip, and they tend to be very large images. So more general GPU memory is important. 768, some data sets may not fit in that. More on-chip memory for sure, and more just raw floating point horsepower by adding more processors down on the chip. It's meant to be scalable that way. I think I'm over time.
Yeah, we should probably stop now. If there's a lot of people interested in asking questions, we can kind of stay seated after people leave and ask questions offline.
And I have some more videos I can show if you're interested.
Okay, so let's do that. If you want to leave, go ahead and leave now, and we'll stop the cameras. Thank you very much.
Yeah.
For information on other online Stanford seminars and courses, please visit study.stanford.edu.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.